Hello and welcome. This week we're going to start talking about a new type of mathematics. We're going to be talking about finite mathematics. Today we're going to be talking about combinatorics, which is a fancy way of saying counting, and then we're going to begin talking about probability. Start very basic. If we have two sets A and B, and if we want to count the number of elements in the set A union B, the formula that we use is the number of elements in A union B is the number of elements in A plus the number of elements in B. And so that we don't count anything twice, we do minus the number of elements in A intersection B. So for example, let's suppose Ali has 3 yellow shirts and 2 blue shirts. How many shirts does Ali have? We know that there's 3 yellow shirts and we know that there's 2 blue shirts. Because a shirt can't be both yellow and blue, we just add these numbers together. So clearly Ali has 5 shirts. The formula is the number of elements in S union M is the number of elements in S plus the number of elements in M. And because a shirt is not both yellow and blue, we don't subtract anything. Next example. In a college, in a university, there are 8 students who are studying mathematics, 12 students who are studying physics, and of these students, 5 of the students are studying chemistry and physics and mathematics. The question is, how many students are studying either mathematics or physics? Let's let M and F denote the sets of students who are studying mathematics and physics. Then the picture looks like this. There is some overlap between the set M and the set F because some of the students are studying both maths and physics. The formula is the number of students who are studying maths, that's 8, plus the number of students who are studying physics, that's 12, but we're counting some of the students twice because 5 of the students are studying both maths and physics, so we do minus 5, and we get our answer 15. The next principle for counting is the multiplication principle. So suppose we have 2 operations, 2 things, which we'll call O1 and O2. Let's suppose O1 can be done in n different ways and O2 can be done in m different ways. Then there's n multiplied by m ways to do O1 followed by O2. For example, let's suppose a man has 5 different shirts, 3 different ties, and 2 different pairs of trousers. In how many different ways can this person wear a shirt, tie, and a pair of trousers? So first he must choose, let's say, a pair of trousers. So that's 2 different pairs of trousers. Then he has 5 different shirts to choose from. So we're going to be 2 multiplied by 5. And then he chooses one of his 3 ties. We multiply by 3. We're multiplying these numbers together because they're all independent. We get 2 multiplied by 5 multiplied by 3, or 30 different choices of outfit. Next example. 4 cities called Aberdeen, Birmingham, Coventry, and Derby are joined by roads as shown above. By how many different routes can a vehicle travel from A to D without going back on itself? What I mean is, just imagine all of these roads are one way, like this. We start at Aberdeen and we want to go to Derby. How many different routes are there? First, let's look at the left picture. Let's suppose we go via Birmingham. It's 4 different ways to go from Aberdeen to Birmingham, but only 1 road from Birmingham to Derby. So So we're going to be doing 4 multiplied by 1, or 4 different routes if we go through Birmingham. Next, let's suppose instead of going through Birmingham, we go through Coventry. There's 2 different routes from Aberdeen to Coventry. There's 3 routes from Coventry to Derby. We're going to be doing 2 multiplied by 3. And then we're going to add these numbers together. If we go via Birmingham, there's 4 different routes. If we go via Coventry, there's 6 different routes. So in total, there are 10 different ways to go from Aberdeen to Derby. How many divisors does 2,800 have? A divisor is a number which divides it. For example, 1,400 is a divisor of 800 because we could calculate 2,800 divided by 1,400 and we would get a whole number. First thing to note is the prime factorization of 2,800. Note that 2,800 is 2 to the power 4 multiplied by 5 to the power 2 multiplied by 7. Or if we add in the number 1, we can think of this as 1 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 5 multiplied by 5 multiplied by 7. To create a divisor of 2,800, we have to use some of these numbers in the red box. First of all, we want to choose some of the 2's. We could choose to use none of the 2's, we could use 1 of the 2's, we could use 2 of the 2's, 3 of the 2's, or we could use all 4 of the 2's. Let's just say, for example, let's suppose we choose 1 of the 2's. Then we look at the 5's. We could use none of the 5's, or 1 of the 5, or both of the 5's. For example, we might say, let's use none of the 5's. And then we come to the 7. And we have 2 choices. Either we use the 7 or we don't use the 7. Let's say in this example we do use the 7. Then we would use the 2 and the 7 and we would get 14. 14 is a divisor of 2,800. The question is asking how many different divisors are there. When we choose how many 2's we use, we have 4 2's. We might choose to use none of them, 1 of them, 2 of them, 3 of them, or 4 of them. There are 5 different choices there. When we're choosing how many 5's to use, 0, 1, or 2 of the 5's. So there's 3 different choices. How many 7's do we use? We can use none of the 7, or we can not use the 7, or we can use the 7. We have 2 different choices. So we have 5 multiplied by 3 multiplied by 2, or 30 different choices. We have 30 different divisors of 2,800. And in fact, I've written these divisors at the bottom of the page. If you count them, you will see that there are 30 numbers just here. We can make a general rule. In general, let's suppose that P1 up to Pm are prime numbers. And suppose that x is P1 to the power K1, some number K1, P2 to the power K2, some natural number K2, multiplied by dot dot dot, multiplied by Pn to the power Kn, for some natural Kn. I should say for some natural number Kn. Then the rule is that x has K1 plus 1, K2 plus 1. So this is a mistake, this should be 1. K3 plus 1 up to Kn plus 1 divisors. So that's the basics, but let's move on to some more sophisticated counting. We're going to be using Permutations and Combinations. First tool we need is a factorial. N factorial, which we write as n exclamation mark, is the product of the first n natural numbers. And just to make it work, we also have 0 factorial, which we say is equal to 1. So, for example, n factorial means n multiplied by n minus 1, n minus 2, multiplied by dot, 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 multiplied by 2, multiplied by 1. And just so that this works for more difficult maths, we also want to say that 0 factorial is equal to 1. For example, 4 factorial means 4 multiplied by 3 multiplied by 2 multiplied by 1, or 24. We're going to be doing things like number factorial divided by number factorial. For example, 7 factorial divided by 5 factorial means 7 multiplied by 6 multiplied by 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1 divided by 5 factorial. We can think of this as 7 multiplied by 6 multiplied by 5 factorial divided by 5 factorial. 5 factorials cancel and we end up with 42. Likewise, and I'll leave this one for you to check, 52 factorial divided by 5 factorial multiplied by 47 factorial is 2,598,960. I want to remark that n factorial gets big very, very quickly. Let's look at these ones. 5 factorial is 120. 10 factorial, 10 is not much bigger than 5, but 10 factorial is more than 3 million. And 15 factorial is more than a British billion or an American trillion. Permutations. Let's suppose you have 4 pictures and you want to arrange them in a line on your wall. 4 different pictures. How many different ways are there to arrange them? Let's suppose our pictures are of cartoon characters. One way to arrange them would be to do Bugs, Daffy, Taz, Tweety. Or let's suppose we want to swap the last 2 around. We could do Bugs, Daffy, Tweety, Taz. Or Bugs, Taz, Daffy, Tweety. Bugs, Taz, Tweety, Daffy, etc. How many different ways are there to do this? If I wrote them all down the list, how many different things in my list would I have? You can think of it like this. First, let's choose the left picture. We have 4 choices. Suppose we make our choice, and then we're going to move on to the second picture. Now there's 3 pictures left. We can choose any one of these 3. So far we've done 4 multiplied by 3. And then we move on to picture number 3. There's 2 pictures left. We could choose either Buggy or Daffy. Multiplied by 2 because there's 2 possible choices. And then when we get to the last one, there's only 1 picture remaining. We only have 1 choice. 4 multiplied by 3 multiplied by 2 multiplied by 1 choice. 4 factorial, or 24 choices. This is the idea of a permutation. A permutation of a set of distinct objects is an arrangement of the objects in a specific order without repeating. And we have a way of writing the number of permutations of n objects without repetition. 2 common ways to write this. We could write this as npn, or a more old-fashioned way, Pnn. In this lesson, I'm going to be using the first one. Theorem. The formula for nPn is this is equal to n factorial. Now let's suppose we still have the same 4 pictures, but we only want to hang 2 of them on the wall. How many different ways are there to hang 2 out of the 4 pictures? This time I'm going to list them all. We could do Bugs and Daffy, Bugs and Taz, Bugs and Tweety, Daffy and Bugs, Daffy and Taz, Daffy and Tweety, Taz and Bugs, Taz and Daffy, Taz and Tweety, Tweety and Bugs, Tweety and Daffy, or Tweety and Taz. In fact, there are 12 ways to hang 2 pictures out of 4. How could we calculate this? Just use the same idea as before. For the first picture, we have 4 choices. After we've chosen one to put in the left picture, we have 3 pictures remaining. So we have 3 choices for the second picture. And that's 4 multiplied by 3 different choices. Or 12, which is what I got when I did my list. How can we write this in terms of n factorial? Well, we have 12, which is 4 multiplied by 3. That's the same as 4 factorial divided by 2 factorial. A permutation of n distinct objects, of which we only take 5 of them. In the previous example, I had 4 pictures, but I only took 2 of them. Without repetition, not repeating the same object, is an arrangement of R of the n objects in a specific order. The notation for the number of permutations of R objects chosen from a total of n objects is npr. And we have a formula for npr, which I will get to shortly. First, suppose that we have 3 objects. And this time I'm going to call the objects A, B, and C. And let's suppose we take R of the objects. Then the possible permutations are shown below. First of all, let's suppose we only take 1 of the objects. We might choose object A, or we might choose object B, or we might choose object C. 3p1, how many different permutations of 1 object taken from the total of 3 objects? There's 3 choices, A or B or C. Instead, let's suppose we take 2 of the objects. I could choose AB or AC, or BA, or BC, or CA, or CB. There's 6 items in this list because 3p2 is 6. There's 6 ways to choose and permute 2 objects out of 3. And finally, how many different ways can we permute all 3 of the objects? Here they are listed: ABC, ACB, BAC, BCA, CAB, CBA. 3p3, 3 permute 3 is equal to 6. Here's the formula. npr is equal to n factorial divided by n minus r factorial. I've put this formula at the top. We're going to use this in this example. Find the number of permutations of 16 objects taken 3 at a time. Here, the total number of objects, or n, is 16, and we're going to be taking 3 of them. So r is equal to 3. In other words, we're asked to calculate 16 permute 3. We put these numbers into our formula, and I'm going to leave it for you to check that the answer is 3,360. Combinations. To start with, let's talk about the Turkish National Lottery. To enter this lottery, you need to choose 6 numbers from a total choice of 49 numbers. The question is, how many different ways are there of choosing 6 objects from 49 objects? And the answer is not 49 permute 6. Why? Because the order of numbers does not matter. When we're playing the lottery, we don't care which numbers come out of the machine. 28, 16, 9, 7, 35, 47. Of course, when we play the lottery, it's the same as 7, 9, 16, 28, 35, 47. So we're not using permutations when we study the lottery. Instead, we're going to use something called combinations. A combination of n distinct objects, taken r at a time, is an r element subset of the set of n objects. The arrangement of the elements in the subset does not matter. And this is the important difference between permutations. When we do combinations, we don't care about what order the objects are arranged in. We have a notation for the number of combinations. We're using NCR in this course. There's 2 other common ways to write it. We could write n over r in brackets or CNR. I'm going to be using the first one, NCR. For example, again, let's suppose we have 3 objects which we are going to call A, B, and C. And let's suppose we take R of these objects. Then the possible combinations looks like this. First of all, let's suppose we take one of the objects. We could choose A, we could choose B, we could choose C. There's 3 different choices, 3 combinations. 1 free choose 1 is equal to 3. What about if we choose 2 of the objects? We could have AB, AC, and BC. Remember that if the order doesn't matter, then BA is the same as AB, CA is the same as AC, and BC is the same as CB. So there's only 3 possible choices. 3 choose 2 is equal to 3. How many different ways are there of choosing 3 out of 3 if the order doesn't matter? Only 1. 3 choose 3 is equal to 1. We have a formula for n choose r. It's n factorial divided by n minus r factorial multiplied by r factorial. It's very similar to the formula for permutations, but we have this extra r factorial term. Again, I've written this at the top as we do our first example. A collector has 20 different coins. How many different ways can 6 coins be selected? In total, there are 20 objects, so n is 20, and we're going to be taking 6 of them. So r is going to be 6. In this question, we're asked to calculate 20 choose 6. We put these numbers into the formula, and I'm going to leave it for you to check that the answer is 38,760. Now, we can answer the lottery question. How many different ways are there of choosing 6 numbers out of 49? We're doing 49 choose 6. put these numbers into the formula, and I will leave it for you to calculate, to check the calculation. There are almost 14 million different ways to choose 6 numbers out of 49. So let's recap. We have permutations and combinations. For permutations, the formula is n factorial divided by n minus r factorial. For combinations, the formula is almost the same, except we have this extra r factorial term. Let's suppose we have 9 people. In how many different ways can we choose a chairperson, a vice chairperson, and a secretary, if we make the assumption that one person cannot hold more than one of these positions? And question 2, in how many ways can we choose a committee of 3 people? Let's look at question 1 first of all. We need to choose a chairperson, a vice chairperson, and a secretary from these 9 people. First, we choose the chairperson. We have 9 different people to choose from, so we make our choice. Then we move on to choosing the vice chairperson. There's 8 people left to choose the vice chairperson. And finally, we choose the secretary. When we choose the secretary, we have 7 different choices. Multiply these numbers together, 9 multiplied by 8 multiplied by 7. There are 504 different ways to choose a committee with a chairperson, a vice chairperson, and a secretary. Or we can answer this problem with permutations. We're using permutations because the order we choose them in matters. The chairperson is different from the vice chairperson, who is different from the secretary. So we're going to be doing 9 permute 3, or 504. Next, suppose we're going to choose a committee of 3 people. Now, the order that we choose them does not matter. We're just choosing 3 of these people. Because the order that we choose them doesn't matter, we use combinations. We're doing 9 choose 3, or 84. I need to remark that permutations and combinations are similar and different. They're similar in that we don't allow repetition, but there's an important difference between them, and it's if the order matters. When the order is important, we use permutations. When the order doesn't matter, we use combinations. You have 2 formulae. The important test for you is when do you use permutations and when do you use combinations. Let's talk about playing cards. A standard deck of playing cards has 52 cards. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, and King. There are 4 suits: hearts, clubs, diamonds, and spades. When we play cards, we're given some cards which we hold in our hands. This is called a hand of cards. So, for example, these 2 pictures at the bottom of the screen are hands of cards. The first question is, how many 5-card hands have 2 kings and 3 aces? Question 2, how many 5-card hands have 2 clubs and 3 hearts? Question 3, how many 3-card hands have all cards from the same suit? Question 1. To solve this, we're going to need to use the multiplication principle and combinations. First, we need 2 kings. In total, there are 4 kings, and we're going to be choosing 2 of them. Doesn't matter which order we get them in, so we're going to be using combinations. We want 4 choose 2. Then, out of the 4 aces, we want 3 of them. We want 4 choose 3. These 2 operations are independent, so we multiply these 2 numbers together. The answer to this question is going to be 4 choose 2 multiplied by 4 choose 3. And I leave it for you to calculate that this is 24. How many 5-card hands have 2 clubs and 3 hearts? How can we get 2 clubs? In total, there are 13 clubs, and we want 2 of them. We also need 3 hearts. Again, in total, there are 13 hearts in a deck of cards, and we want 3 of them. So we're going to be doing 13 choose 2 multiplied by 13 choose 3, which it turns out is equal to 22,308. How many 3-card hands have all cards from the same suit? There's 4 suits in a deck of cards: hearts, clubs, diamonds, and spades. And each one of these suits has 13 cards. Let's suppose we just think about hearts. How many 3-card hands have all hearts? There are 13 hearts, and we want to choose 3 of them. 13 choose 3, or 286. But there are also 13 clubs in a deck of cards, so the calculation must be the same. There's also 286 3-card hands, which are all clubs, 286 3-card hands, which are all diamonds, and 286 3-card hands, which are all spades. We want to do 286 plus 286 plus 286 plus 286, or 4 multiplied by 286, which is 1,144. Next example. A bag contains 2 white balls and 3 red balls. In how many ways can 3 balls be chosen if at least 1 ball must be white? So if at least 1 ball must be white, then there's 2 possibilities. We have 1 white ball and 2 red balls, or 2 white balls and 3 red balls. Sorry, 1 red ball. How many different ways are there to get 1 white and 2 red? 2 choose 1 to get 1 white, and 3 choose 2 to get 2 reds. How many different ways are there to get 2 white balls and 1 red ball? 2 choose 2 multiplied by 3 choose 1. And then we add these 2 numbers together. 2 choose 1, 3 choose 2, plus 2 choose 2, 3 choose 1. And I'll leave it for you to check that the answer is 9. Now let's suppose you have 1 red ball, one blue ball, one green ball, and 3 orange balls. And for this question, we're going to assume that the 3 orange balls are identical. How many visually different ways are there to arrange the balls in a line? If we had 6 different colors, then this would be easy. 6 permute 6. 6 objects, change the order of them however we want, we get 6p6. However, that's not the answer to this question because we have 3 orange balls. So the correct answer is going to be less than 6p6. For example, if we label the balls RBG for red, blue, green, and then O1, O2, O3 for the orange balls, then these 2 different ways of arranging them would look the same if the orange balls are all identical. But if we did 6p6, we would be counting these arrangements twice. And we don't want to do this. We don't want to count them twice. We want to count them only once. How many different ways are there to arrange the orange balls? 3p3, or 6 different ways to arrange the orange balls. This means that if we calculated 6p6, we're counting each arrangement 6 times. So the answer to this problem is going to be 6p6 divided by 3p3, or 120. Let's do a similar example. In how many different ways can the letters of the word mathematics be arranged with the extra rule that all of the vowels are consecutive or next to each other? The word mathematics has 11 letters. That's 4 vowels and 7 consonants. But the rule is these 4 vowels, which are colored in orange, must always be next to each other. What we're going to do is we're going to group these 4 vowels together, and we're going to think of it as a single object. So in other words, instead of thinking we're doing a problem with 11 objects, we're going to think that we're doing a problem with only 8 objects. And our objects are MTH, MT, CS, and the vowels. First question is, how many different ways are there to arrange these 8 objects? Of these 8 objects, some of the letters are repeated. We've got 2 M's, 2 T's, 1 H, 1 C, 1 S, and 1 vowels. How many different ways are there to arrange these 8 objects? If the 8 were all different, it would be 8p8, but they're not all different. We have 2 M's. We need to divide by 2p2 to take care of this. We also have 2 T's. So count for the 2 T's, we also need to divide by 2p2. We get the answer, about 10,080 different ways to arrange these 8 objects. We're not finished yet. We need to ask, how many different ways can the vowels A, E, A, I be rearranged? If these 4 vowels were all different, it would be 4p4. But they're not all different because we have 2 A's. To count for the 2 A's, we need to divide by 2p2. There are 12 different ways to arrange the vowels. And then we multiply these 2 numbers together. 10,080 multiplied by 12. Before I finish this chapter, let me point out, if you have a scientific calculator, look on it and look for NPR and NCR. This is a picture of a Casio calculator, and this one happens to have NPR and NCR on the multiplication and division buttons. Perhaps the best online calculator or the best smartphone app for maths is Wolfram Alpha. If you go to this website or use this app on your phone, try typing things like 7 permute 3 and 7 choose 3. Our final chapter for today is an introduction to probability. Next week's lesson will be all about probability. This week we're just going to do an introduction. Let's suppose we have a single die which we roll. What are the possible outcomes of rolling a single die? What are the numbers that we could get on top of the die? We can get a 1, a 2, a 3, a 4, a 5, or a 6. The set of these possible outcomes is called a sample space. Each one of the numbers in the sample space is called a simple event. Now let's suppose we want to roll an even number. We're interested in the subset 2, 4, and 6, the even numbers. This is called a compound event. The set S is called a sample space for some experiment, if and only if. S contains every possible outcome of the experiment, and if we know that one and only one of the outcomes in S must occur. An event is a subset of S, and we include the empty set and S itself. Small ei is a simple event. A compound event is a subset of S which contains more than one element. Now let's suppose we have 2 dice and we're going to roll them. What are the possible outcomes of rolling 2 dice? The first die could be 1, 2, 3, 4, 5, and 6. The second die could also be 1, 2, 3, 4, 5, and 6. So we might have 1, 1, or 1, 2, or 1, 3, or 1, 4, etc. You can see from this table that there are 36 different possible outcomes of rolling 2 dice. The sample space will be the set containing all of the pairs A and B, where each one of A and B is a number between 1 and 6. Question: what is the event which corresponds to a total score of 7? How can we get a total score of 7? I could have a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, and a 6 and a 1. What is the event which corresponds to a total score of 3? How do we get 3? 1 and 2, or 2 and 1? What is the event which corresponds to a total score greater than 10? 5 and 6 gives 11, 6 and 5 gives 11, and 6 and 6 gives 12. And then finally, what is the event which corresponds to a total score of 2? The event is the set containing 1, 1. This one contains only one element. This is a simple event. The first 3 subsets contain more than one element. They are compound events. Let's suppose we have a sample space which contains n simple events. The probability of an event occurring we denote as P of E. There's 2 rules that we must have. Every possibility must be between 0 and 1, a closed interval from 0 to 1. And if we add up all of the probabilities, we must get 1. For example, let's suppose that we're flipping a single coin. Sample space is heads or tails. And if we have a fair coin, we can assume that the probability of getting a head is a half. The probability of getting tails is also a half. Note that both of these probabilities are between 0 and 1, and if we add them together, a half plus a half is 1. If we flip this coin 1,000 times, we would expect to get heads roughly 500 times. The probability of an event, which we say P of E, must satisfy the following 4 rules. If E is the empty set, the probability must be 0. If E is the whole sample space, the probability of E must be equal to 1. If capital E is a simple event, the probability of capital E must be the same as the probability of small ei. And if capital E is a compound event, the probability of capital E must be equal to the sum of the probabilities of all of the simple elements in E. For example, if capital E is the compound event containing A, B, and C, the probability of E must be the probability of A plus the probability of B plus the probability of C. Probability of E equal to 1 means that event E is certain to occur. If we have that the probability is equal to 0, that means that the event E will never occur. Now let's suppose we have 2 different coins. The sample space is now the set containing 4 elements. We might have heads, 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 tails, tails, heads, and tail, tail. And we're going to assume that these are all equally likely. The probability of each of these simple events we're going to assume is equal to a quarter. What is the probability of getting 1 head and 1 tail? What is the probability of getting at least 1 tail? What is the probability of getting at least 1 head or at least 1 tail? What is the probability of getting 2 tails? What is the probability of getting 3 tails? First of all, how can we get 1 head and 1 tail? We could have head tails or tails head. Probability of this compound event must be a quarter plus a quarter or a half. How can we get at least 1 tail? We could have head tail, tail head, or tail tail. A quarter plus a quarter plus a quarter or 3 quarters. How can we get at least 1 head or at least 1 tail? We could have head head, that has at least 1 head. Head tail has at least 1 head. Tail head has at least 1 head. Tail tail has at least 1 tail. We have the whole sample space S, and the probability of the whole sample space must be equal to 1. What is the probability of getting exactly 2 tails? We must have a quarter. What is the probability of getting 3 tails? This is not possible. It's not possible to get 3 tails, so our event is the empty set, and the probability of the empty set is 0. If we assume that every simple event in S is equally likely, then the probability of an event E is the number of elements in E divided by the number of elements in S. And we've been studying this, we've been studying counting. So we can do examples using this assumption. Again, let's suppose we have two dice, and let's suppose that each simple event is equally likely. Suppose that the dice are fair dice. Find the probabilities of a total score of 7, a total score of 3, a total score greater than 10, and a total score of exactly 2. These are the same things, same events that we talked about earlier. How do we get a total score of 7? We've studied this earlier. The event is 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, or 6 and 1. There are 6 elements in this compound event. There are 36 elements in the sample space, so we're doing 6 divided by 36, or 1 over 6. How do we get a total score of 3? There are now 2 elements in our compound event, so we're doing 2 divided by 36. A total score which is greater than 10. Our compound event has 3 elements, so we're doing 3 divided by 36. How do we get a total score of exactly 2? Only 1 element in our event, so 1 divided by 36. Back to playing cards. For the final example of today's lesson. You randomly draw 5 cards from a standard deck of 52 cards. What is the probability of getting 2 clubs and 3 hearts? The first thing to ask is, how many different 5-card hands are there? How many different ways are there of choosing 5 cards from a total of 52? We know this because we're going to use combinations. There's 52 choose 5 different ways to get 5 cards out of 52. And we've already studied this example earlier. We've already studied that there are 13 choose 2 multiplied by 13 choose 3, 5 card hands which include 2 clubs and 3 hearts. Put this information together. We're going to be doing 13 choose 2, 13 choose 3, divided by 52 choose 5. And I'm going to leave it for you to check that if we calculate these, we get 0.0062, which is a small probability. And that is the end of this week's lesson. Next week, we'll move on to some more advanced probability topics when we study chapters 20, 21, and 22. Are there any questions?